Welcome to MEI Mechanics. We're on the topic Impulse and Momentum 1, Introduction, and this is video 1.3, Conservation of Momentum. So when we're dealing with collisions between objects, what we're going to do is assume that there are no external forces acting and just consider the momentum of the objects, and of course that depends on the mass and the velocity. And this is velocity, of course, being a vector quantity which has a direction as well. And it's measured in Newton seconds. And as we've been seeing, we often are interested in the change in momentum, so the final momentum minus the initial momentum. And just a reminder as well that momentum is not a measure of energy. Remember, of course, as well that there's a kind of parallel between what happens with work done being force times distance, and that gives us a change in energy, and impulse, which is a force times time, it gives us a change in momentum. So what do we mean when we're talking about conservation of momentum? Well, suppose these two particles collide. So before the collision, they each have an initial velocity. So we'll call this one u1, this one u2. Obviously, they'll have to be different, otherwise they won't collide. And in fact, in this case, u1 would have to be more positive than u2, so that they're in some sense moving towards each other, getting closer. And then after the collision, they'll both have changed their velocities, so they'll both have a new velocity, v1 for particle 1 and v2 for particle 2. Now, if we think about impulse now, and this really comes from Newton's third law if you think about it, because the force on one particle due to the other must be the negative of the force on the other particle due to it. So even when you multiply that by time, this collision, the time is the same for both particles, so that means the impulse is going to be equal and opposite. And so what that means is that the change in momentum of particle 1, it must be the negative of the change in momentum of particle 2. So that means we can combine these two equations together, eliminating I, and rearrange to make this, which is essentially saying that the total initial momentum, those are the momentum of the two particles before the collision, is equal to the total final momentum. And so that's called conservation of momentum, because it's the same value before and after. Now, just to point out, when we're thinking about impulse, you may imagine collision sometimes not really happening over any time, just instantaneous. And of course, in reality, that's never really true. It's just a very, very short time. And what that means is that for a sort of average size of impulse, if the collision happens over a short time, it means that the forces can be very large, surprisingly large forces involved when objects collide. So in this first example, what we have is two particles. They've got different masses. They've got the same speed, but that speed is in different directions. So they're moving towards each other, each at the speed of 4 meters per second. And what happens in this example is that they're going to coalesce. That means that they're not going to bounce off each other. They're going to stick together and just form one particle. So imagine that these things are maybe coated in some kind of sticky coating. That means that when they collide, they just form one thing. So before the collision then, what have we got in terms of momentum? Well, we have 4 times 3, and we have, from this one, we have minus 4 times 2. So that's the momentum of this object plus the momentum of that object. And so that total momentum is 12 minus 8, which is 4 Newton seconds. So after the collision then, we've just got one particle. So we're thinking of this as one particle. I could draw these two stuck together. We could imagine maybe it's maybe the drops of liquid that have coalesced into one larger drop. However you want to think about it, but obviously because that's come from a mass of 3 and mass of 2, that's got a mass of 5 kilograms. Now we're gonna, if we think about it, because this is the larger one, we know actually that this is going to end up with a velocity directed to the right. But even if we didn't know that, we could define that being to the right, and then a negative value we could interpret as travelling to the left. And that's a velocity of v. So that final momentum is 5v, and that must be, by conservation of momentum, that must be equal to the initial momentum. So 5v must equal 4, and so the final velocity v of this single object is 4 divided by 5, which is 0.8 meters per second. Now in the second part of the question, we're asked to find the impulse on each mass when that happens, when they stick together and coalesce. Now remember, the impulse is just the change in momentum. We can see that the initial momentum of this 3 kilogram mass is it's going to be 3 times 4, and the final momentum is 3 times 0.8. So the change in the momentum is 3 times 0.8. That's the final momentum of that, minus the initial momentum, which was 3 times 4. That's minus 9.6 Newton seconds. So defining right as being positive, then this is negative. That means that the impulse acting on this thing is directed to the left, which sort of makes sense because it's moving to the right to begin with, and then after the collision it's moving to the right a bit more slowly. So to do that, it must have been pushed in a leftward direction in order to slow it down. Now then, for the 2 kilogram mass, we do a similar thing. Again, just being careful with our signs. So its final momentum is 2 times 0.8, because it's part of that coalesced body with travelling at 0.8 meters per second. That must be its speed, and it's got a mass of 2. Then minus the initial momentum of this object. Now because that was moving to the left, its initial momentum was 2 times minus 4. And that works out as positive 9.6 Newton seconds. Now notice that they are the same size as each other, and that's certainly not a coincidence. That is exactly what you should expect. Again, through Newton's third law, you expect the impulse on one object to be the negative of the impulse on the other object. Now, in this second example, the objects are no longer coalescing. They're bouncing off each other. So the initial setup is exactly the same as it was before, and so we know that the total momentum before the collision is 4 Newton seconds, and after the collision the total momentum is the momentum of the 3 kilogram mass, so that's 3 times 0.4 plus the momentum of the 2 kilogram mass. Notice, by the way, that 0.4 is still in the positive direction, and then that is 2 times v, where v is this unknown as yet velocity of the 2 kilogram mass. I'm referring to it as velocity because even though in this situation it's going to have to be moving to the right, in general we wouldn't know if it was moving to the right or left after the collision. So we call it velocity, and then define the speed, we would just write the positive of that if it happened to be negative. And by conservation of momentum, that final momentum must be equal to the initial momentum, which we know is 4 Newton seconds. So we have an equation now that will give us this final velocity and hence the final speed. That works out as 1.4 meters per second. Now this final example, a little bit different from the previous one. So we've got now a 2 kilogram mass and an unknown mass of m kilograms. And this unknown mass here is at rest initially. After the collision, it's this mass here which has come to rest, and this mass is moving with a speed of 4 meters per second. And we need to see if we can use that information alone to work out what this unknown mass is. So we'll just start in the same way as we always have. So we'll start by writing down the initial total momentum. Now, obviously this one is 2 kilograms times 6, so it's got an initial momentum of 2 times 6, and then plus the initial momentum of this, which is m times 0. So that is 12 Newton seconds, the initial momentum. Then after the collision, the momentum of this particle is 2 times 0, and the momentum of this one is m times 4. And by conservation of momentum, that must be equal to the initial momentum of 12. And so we can easily then from there see that m must be equal to 3 kilograms. So that concludes video 1.3 on conservation of momentum. The final video on this topic will be 1.4, momentum and impulse in 2D.